All right, good afternoon. So this is the asynchronous lecture for March 19th, Stat 252 lab. In today's lab, we're going to learn how to conduct a simple linear regression analysis in in SPSS. The questions that we are going to utilize for this announcement are shown here on this Word page. So we're going to use the SPB, or that should be SBP.SAV dataset, which is available on the course website. So for this dataset, we are going to explore the relationship between SBP, which is our response variable, and age, which is our explanatory variable. The first thing we're going to do is build a scatter plot of these two variables. So we're going to place the response variable on the y-axis and the explanatory variable on the x-axis. We're going to use the scatter plot to comment on linearity, which is the first assumption of the simple linear regression model. Then we are going to fit a simple linear regression model to the data set, and we are going to report the estimates of the model with the 95% intervals. We are also going to give the model itself. Then we're going to evaluate the assumptions of the SLR model used in part B. So we're going to talk about linearity again. Then we will talk about constant variance and normality and the simple random sampling assumption, which would be verified using a description of the data set. Finally, we will conduct a model utility test. So this is basically just a test about beta 1. And then we'll give the coefficient of determination and interpret the value. Okay, so in SPSS, we're going to upload our data set. So again, we're using this sbp.sav data. As per usual, we will open that in SPSS. Okay, so you can see that this data set is comprised of two variables, SBP and age. All right, so our objective is to model SBP as a function of age using a simple linear regression model. So the first thing that we would want to know is, does it actually seem reasonable to use a simple linear regression model to relate SBP to age? So to answer this question, we go graphs, legacy dialogues, scatter/dot. Okay, so we're building our scatter plot between SBP, which is the response variable, so the y-axis variable, and age, which is the explanatory variable, so the x-axis variable. Okay, so simple scatter, define. All right, so on the y-axis, we place SBP. On the x-axis, we place age. And then in titles, we'll just want to say scatter plot of SBP versus age. Click continue, click OK. Okay, so here is our scatter plot. All right, so we're just going to copy and paste this into our Word document. Okay, so we have insert file. Desktop, screenshot, boom. All right, so here's our scatter plot of SBP versus age. So basically all we're doing here is we're checking to see if the scatter of the points appears to be linear. So what you want to ask yourself is, if I was to stick a straight line through the middle of this data, does it seem like those points follow the line? Now, in this particular illustration, I think it's pretty clear that this data is showing a positive linear relationship. So as age is getting larger, SBP is also getting larger. Further, if we put a straight line through the middle of this data, that seems reasonable. So we don't see any obvious curvatures in the points. So this is similar to actually how we would evaluate a normal probability plot. So we're looking for that straight line pattern. Now, obviously the points aren't directly on the line like we would need for a normal probability plot, but that's okay for the purposes of what we're doing because we will account for that dispersion from the line in the modeling process. So in part A, we can say something to the effect of the scatter plots of SBP versus age shows a positive linear relationship. That is, as age increases, SBP also increases. Okay. All right. So therefore, it is reasonable to use a simple linear regression model for this data. Okay. That is basically what we're saying is it is reasonable for us to use a model that fits a straight line to the data for this particular data set because the points appear to follow a straight line. Okay, in part B, we want to give the estimates of the slope and the y-intercept with 95% confidence interval. So what we're going to do here is actually estimate the simple linear regression model that relates SBP to age. So to do this, in SPSS, we click Analyze Regression Linear. Okay, so we have Analyze Regression Linear. All right, our dependent variable is the response variable. So this is going to be an SBP, and age is our independent variable. So we put this here. Now we click Statistics. Under regression coefficients, we'll have estimates, confidence interval. So that gives us 95%. All right. And then we have model fit selected here. Click Continue. Click OK. All right, so you can see that this pops out a number of different values. So we have model summary, we have ANOVA, and we have the coefficients. So for part B, we're going to use the coefficients. So we're taking this information here. Sorry, I keep slipping to the, I'm just going to close this so I don't do that anymore. Okay. And then we're going to insert picture from file, screenshot number 2. All right, so from the output, we have the following. We have B0 is equal to 98.715. We have B1 is equal to 0.971. So our fitted SLR model is given by, and now we're going to have y hat subscript I Does this thing let you do? Okay, I might abandon this idea momentarily. Oh, here we go. So here it is. So we'll have y hat okay, so it's not going to let me do it like that. So I'll just do it this way. So we're going to have y hat subscript I is equal to, this is an I right here, is equal to B0 plus B1 x1. So that's 98.715 plus 0.971 x subscript I. All right, so that's our this is the fitted SLR model. So this is our estimates of the population parameters beta 0 and beta 1. All right, we're also asked to give the 95% confidence intervals for beta 0 and beta 1. You can see that those are provided here. So we have the 95% confidence interval for B0 is 78.230 to 119.2. So we are 95% confident that the population y-intercept is between 78.230 and 119.2. This also means that we are 95% confident that the value of SDP, that the population value of SBP when age is 0 is between 78.230 and 119.2. The 95% confidence interval for B1 is, I guess I don't need the brackets here, do I? No, let's leave them. Is 0.540 to 1.401. So we are 95% confident that the population slope is between 0.540 and 1.401. This also means that we are 95% confident that the that for every 1 unit increase, or rather for every year an observation ages, the SBP increases by 0.540. Just going to move this up a bit so I can get. There we go. Okay, so that's part B. So we fitted our regression model. You can see that we're literally just pulling the output directly from the model. All right. And then these are the 95% confidence intervals also pulled directly from the output. And these are just the corresponding interpretations of those intervals. Okay, so that brings us to part C. In part C, we're asked to evaluate the assumptions of the SLR model used in B. Okay, so there are 4 assumptions. 1, linearity between the response variable and the explanatory variable. 2, the observations were collected via simple random sampling. Okay, so that's just the standard simple random sample assumption. So we're assuming the observations are independent of one another. The third is that the population response variable is normally distributed, and that the, I guess we can just say the response variable is normally distributed, and the response variable has constant variance, which we can call sigma squared. Okay, so for each assumption, for assumption 1, we evaluate this using a scatter plot of the data. So for this assumption, we can just say C question 1C for validation. Right, so for the linearity assumption, we only require the scatter plot to determine if it appears like there's a linear relationship. For part 2, this would be done via a knowledge of the experimental design. right? So for part B, the lab manual tells us that that we have a sample. It just says a sample of 30 individuals. So let's just assume sample was collected via SRS. All right, and then for part 3, the response variable is normal. The response variable is constant variance. Okay, so for part 3, or for assumption 3 and assumption 4, we're going to need to use residual analysis. So this is something that we will set up in SPSS. For the normality assumption, we will be using a normal probability plot of the residuals. For the constant variance assumption, we will be using a scatter plot of the residual values against the predicted values from the fitted line. Okay, so to do that, we go back to SPSS. So we'll start by computing the values that we need. So we go analyze, regression, linear. So we're using the same path that we used before. Now we go to save. All right, so analyze, regression, linear, then we click save. We want unstandardized predicted values and we want standardized residuals. Okay, so unstandardized predicted, standardized residuals. All right, we don't need the covariance matrix, but we'll keep it anyways. Click continue, click OK. So you can see that this reproduces the output that we had before. But in our table, we now have the predicted values and the standardized residuals. So for the normality assumption, we will go analyze, descriptives, QQ plot. So this is our usual approach for validating normality. And we are going to use the standardized residuals as our variable against the normal distribution. So again, the usual approach that we take for validating or for checking the normality assumption. Okay, so here's our QQ plots. Okay, so we'll add that into our file here. Okay, so this QQ plot doesn't look great. This is showing us, so the normal probability plot is showing that the data has heavy tail behavior. This suggests that the normal distribution is not, that the normality assumption or rather this suggests that there is evidence that the response variable is not normally distributed. All right. Further, it suggests that the response variable could be potentially student T distributed. The second part is a little bit of food for thought, so we shouldn't really make this kind of statement. All that really matters to us is that there is some evidence that the data is not, that the variable is not normally distributed. But you can see, like, when you evaluate this kind of shape, this is sort of like an S-shaped behavior. So you can see that we have this lower tail activity here, then we get a large portion that kind of follow the line, and then we have this upper tail activity here. That's usually representative of a heavier tail distribution, like a student T distribution with a low degree of freedom. Finally, you notice this 1 point over here. So we can also say the normal probability plot gives evidence of one outlying observation. All right, so it doesn't seem like normality. It seems like there's evidence to suggest that the data is not normally distributed. But as we know, this is how it goes a lot of the time. All right, now we want to check the constant variance assumption. So to check the constant variance assumption, we're going to build a scatter plot of the residuals versus the predicted values from the line. So we go analyze, or sorry, we go graphs, legacy, scatter. So the same thing we did for 1A, simple scatter. All right, our Y value will be the standardized residuals, and our X value would be the unstandardized predicted values. And here we have scatter plot of residuals versus predicted values. Continue, click OK. All right, so what we're looking for here is essentially just random noise. So we just don't want to see any evidence of a pattern. All right, so if we take this plot, insert this here. Okay, so when we look at this plot, we can see again there's evidence of an outlier. So we can see that we have this point here, which is most likely the point that's shown here, right? So that's indicating that there's a value that could be outlying from the group. When we look at the rest of the data, this is what we would like to see. So this is basically what we refer to as kind of a cloud-like shape. So you want the data to look like they're just sort of randomly sorted, and there's no apparent trend. So we can say here, the scatter plot of the residual versus predicted values show that there is one potential outlier, but that there is no obvious trend. Therefore, we can conclude that there is no evidence to suggest that the variable of interest does not have constant variance. Right? So again, we want to see this cloud-like behavior in the residuals. That's the ideal situation. All right. Part D says, conduct a model utility test at the 5% significance level. All right, so first off, we have the assumptions of the test. These are the same assumptions that we validated in part C. Okay, so here we can just say, sorry. So here we can just say C. All right, now we can actually work out the model utility test. Now, the funny thing about the model utility test is it's just a general test about the slope. So we have H subscript 0, that's a superscript. And then we're gonna have beta 1. One equals 0 versus H subscript A, beta 1 not equal to 0. So on step 2, we give the significance level. So we're going to have here alpha equals 0.05. On step 3, we give the test statistic. So the test statistic is actually given in the same output that we use for the confidence intervals in part B. So we can just take our coefficient output here. All right, and then we can see that T is equal to 4.618. So the value in the first line is the intercept numbers. The value in the second line are the slope numbers. We want the T value that's associated with the intercept. On step 4, we take our P value, which is right beside the T value. So we have T 4.618. The significance here, that's our P value, 0.000. And on step 5, we would have reject H0. All right. And then on step 6, we would have at the 5% significance level, the data provide sufficient evidence to suggest that the fitted SLR model, I'm just going to check my language real quick to see. Yeah. Basically what we're saying here is that there's evidence that the model is useful or that age is useful as a linear predictor for SBP. So we can write at the 5% significance level, the data provides sufficient evidence to suggest that age is a useful linear predictor for SBP. All right, so that's the model utility test. Again, it's just a test of the slope being equal to 0. And the idea here is essentially if there's no evidence to reject the null, that means that there is evidence, or if there's no evidence to reject the null, that means that beta 1 could be equal to 0, which would mean that y is equal to beta 0 plus 0. So x has no effect. But since we have rejected the null, we're saying there's evidence that beta 1 is different from 0, which means that there is evidence that age forms a linear relationship with SBP in this case, so it's useful as a linear predictor for age. Okay, the last part is determine the coefficient of determination and interpret the value. So in our SPSS output, when we went analyze, regression, linear, in the statistics column, we had model fit selected. So when we clicked OK, we had the following output produced. So I'm just going to scroll up to show this to you. Okay, so here's our coefficient table. We have an ANOVA table that's shown here. And then in model summary, you can see we have R and we have R squared. All right. So the coefficient of determination is the R squared value. So we're going to take our model summary page here. We are going to insert that here. All right. And then we can say R squared is equal to 0.432. Okay. Therefore, the fitted SLR model explains 43.2% of the variation in the response variable. And that's our stock interpretation of the coefficient of determination. So the coefficient of determination, again, is a value between 0 and 1, and it is telling us how much of the variation in the response is explained by the fitted model. So in this case, 43.2% of the variation in the response is explained by the fitted regression model. All right, so that's all the material I wanted to cover with you today. This will be sufficient to complete question 1 on assignment number 5. So next Friday in lab, we will discuss question number 2, which is the MLR, or multiple linear regression question, and that will be sufficient for question 2 in assignment number 5. All right, so I hope you guys have a good weekend. If you have any questions, just mark down, where the question came up on the video, and just let me know. Say like at this particular time you said this, or just let me know, what I said that you wanted clarification on, and I will get back to you as soon as I can. So have a good weekend, and I will talk to you guys next week.